Hello everyone, my name is Simon.
My name is Yuan.
Today we are presenting our project, Detecting Cancers in Gigapixel Pathology Images.
In this presentation, we will start with the problem and talk about how we process our data, train the model, and discuss the results. Finally, we will go through our code. First, let's talk about problem description. Imagine you are a doctor. You want to find tiny tumor cells in a gigapixel pathology image. It's extremely difficult and time-consuming, so we want to develop a framework to assist physicians to locate tumor cells and furthermore, reduce the misdiagnosis. The picture on the left is a small patch contains cancer cells. The middle one is the annotation by the professionals. The last image is the prediction of our model. The prediction by our model is very fast, but we get a similar result. Before we jump into details, let's have a quick overview of our project. We started by reading the gigapixel level slides and masks, cut them into small patches, and use them to train our model. Once we have our model, we can use them to predict masks of test patches. Then we need to stitch the small mask patches created by our model into one big gigapixel mask. Next, let's talk about image processing. It's extremely hard to use the huge image as an input for our model. As you can see, the level 0 is the dimensions of the original image. So we divided the slide into small patches. The size of the patches is 256 by 256 and the stride is 128. Smaller stride will produce more patches with cancer cells. Finally, we choose level 345 because it provides enough training data sets for the model. After converting the small patches, we find that only a small part of them contains cancer cells, which leads to data imbalance and slows down the training process. Our solution is to filter out the patches without cancer cells. Now we encounter the new problem of fewer training data. In order to produce more training data, we use data augmentation. The left image is the original patch, and we rotate it by 4 multiples of 90 degrees. Apply a left-right flip and repeat the rotations.
Now let's talk about the model. When we first think about this project, we immediately think about using a model like Inception because it is a project dealing with images. However, after some trial and error, we realized Inception is good for image classification because it can extract filters from the image. However, we treat this project as an image segmentation problem, so we switch to UNet. The UNet combines the location information from the downsampling path, and in the upsampling path, it obtains the general information combining localization and context, which is necessary to predict a good segmentation mask. So we have the input image size of 256 by 256 by 3, and we want up to the same size mask, but only contains one single channel. We use the binary cross entropy as our loss function. For metric, we start with IOU, intersection over union. However, we notice that there's only a small increase during the training process. So we switch back to accuracy so that we can better present our result. We start with a single tower model, as you can see on the left. We train the model, and once we have a good result, we want to utilize the benefit of different levels of patches. So we build a multiple tower model to see if we can get a better result. Here's our result. On the left, we have the gigapixel input image staged by small patches, and the ground truth is shown in the middle. On the right, we have the predicted mask generated by the models trained with 3 different levels of patches, as you can see in color blue, yellow, and green, indicate the level 3, 4, and 5. This is our training curves, we trained all 3 levels with 10 epochs. Now let's go through our code.
Here's the file about pre-processing. We use a library called OpenSlide to read slide and mask. Here's the general information about the slide and mask. And we show the picture at level 5, level 4, and mask at level 4. And we combine the slide and mask into one image to indicate the position of the cancer cells. And here we define a function to convert the slide into small patches. We set the stride to 128 and the size of the patch into 256 and 256. We set a threshold here to filtering out the patches without the cancer cells. If the patch contains a cancer cell, we will save the slide patch and the corresponding mask together. And here we convert the slide into level 5 and level 4 and level 3. Second file is about the data augmentation. We read the patches from our dataset and rotate the original image by 4 multiples of 90 degrees. Then make a flip to create 8 different images as our datasets.
Here we have our single tower model. We start with reading the image and mask from the folder, load them, create into a data set. We use these 2 functions to decode images. And here we separate them into train test dataset and do the batch, shuffle, and cache. Here we create some help functions to showing the result during the training. Here we define our UNet model. Here is the prediction before the training, and we start our training here. This is the dataset without augmentation, so we are training 50 epochs. Here's our final result doing prediction on test dataset. And you can see you can get pretty good result here. So we use this as our starting point to build our multiple tower model. We are doing very similar process here with low images. However, we are doing 3 different datasets at level 3, 4, and 5. We use same function to decode image. And we create the dataset with train test and a validation. Here we create the same UNet model. However, we have 3 models here right now. We have level 3 model, level 4, and level 5. Same helper function, and we are training level 3 here. Since this is the data with augmentation, we're only training 10 epochs. This is our learning curve for model level 3, level 4, and level 5. Now let's see our result. Here result for test slide 031. We're reading the slide, reading mask, comment together to see we can get correct information. We cut them into 3 different level patches. We load all 3 models as we saved the file before. And now let's jump to result. Here we're doing prediction on the model we saved and stitching them together to create a gigapixel mask. On left we have input image, true mask, our prediction. This is level 3, level 4, level 5, and combine them together to get our final result more like a heat map. Now we're doing the same thing to the different test slide. It's 078. Let's jump to result. We have level 3 prediction, which is very accurate. Level 4, level 5, combine them together. This is our last test slide, 064. Let's jump to result. We have prediction on level 3, level 4, and level 5, combine them together. And as we can see, we can get very accurate result on level 3. We think this is due to that level 3 has a big zone level, so it can see the tumor cells in much greater details. That's all for our project. Thank you.
Thank you.